Okay, guys, welcome back. We're going to talk a little more complicated versions of U substitution. We didn't get to a ton of examples in the first video, but I'm going to link some more videos from guys like Patrick JMT. Khan Academy is always a place to go. I kind of steer clear of them for some reason. But Organic Chemistry Tutor is another guy that does a really good job of providing examples. So I'm going to just send some links to those videos, or you can go seek them out on your own so you can see some other examples of U substitution. Just want to reiterate some ideas of U substitution. It's when we see a function that really doesn't fit a pattern, but through some replacing complicated items with more simple items like a U, we give it that extra little helping hand to get the ball rolling. But some, you got to do a little bit more. And I want to show you some more complicated examples because you'll see more complicated examples on the homework set. So again, the U is normally we want to start by picking the inside function as the U. That's like the most common choice for U, but that's not always the case. Sometimes you've got to ask yourself, well, is one thing the derivative of the other? If the one thing is the derivative of the other, then I can use U substitution to simplify that expression. There's other times, though, that once you select a U, you're going to have to manipulate the U. So I'll show you a couple of examples I mean by manipulating the U. So let's start off with the integral of x plus 2 times the square root of x minus 1. Can't really do anything with this algebraically. Can't really send in x plus 2 into the radical. Can't distribute the radical to the x plus 2. There's nothing here that's the derivative of anything else. So we kind of feel stuck with how to proceed. But let's try U equals to x minus 1. And I want to do that because I want to get rid of, that is the function within the function, right? Where it's inside of a square root. Let's start there. So du is just dx. Simple, easy swap there, right? Nothing needs to happen. We don't need to multiply by anything. We don't need to do anything crazy. So we'll set this up as our U filter and send in the function. So here we go. We've got the integral of, let's see, we got x plus 2 doesn't get changed, but we get the square root of U, and then dx just swaps over to du. So here's a little bit of a conundrum. What do I do with the x plus 2 in order to swap it over in terms of U? Well, you saw a little bit of this on that introduction from last week, the U substitute. Sometimes we're going to have to play the game where we solve for x. And if U is x minus 1, then x is U plus 1. So now anytime I have a singular x, I can always replace it with a U plus 1. So x plus 2 becomes U plus 3. Well, now we've done it, right? Now we've replaced all the x's with u's. Let's see if we can go a little bit further here. So I'm going to distribute the square root of U now to U plus 3 because it's just a thing. I can do that now. So I have U to the 3 halves plus 3U to the 1 half. Well, now the story goes, power rule. This is simple. Power rule is going to be the way to go. So the antiderivative now, you can see a lot of that manipulation is replacing, using algebra, distributing. We really haven't even begun to integrate, but we'll use power rule to do that. So U to the 5 halves multiplied by 2/5 plus 3 times U to the 3 halves multiplied by 2/3, which that'll simplify down to 2, add our constant of integration. So let's kind of see what this looks like back in terms of x. So that'll look like 2/5 times the quantity x minus 1 to the 5 halves plus 2 times x minus 1 to the 3 halves. And there is a great looking antiderivative to something that looked pretty gnarly at the start. Looked like we couldn't go anywhere. But that game-breaking play right here, let me highlight it for you. Right here, the game-breaking play turned out, the GBP turned out to be the swapping, like the manipulation of u, solving u in terms of x, so we can, or for x, and so we can swap that out as we did here. So that was fun. How about another? So here we see a rational expression. And let me give you a rule. So a rule is going to be, a good rule of thumb to follow, is if the degree of the numerator in a rational expression is greater than or equal to the degree of the denominator, you must long divide first. Now, long division is probably not your favorite thing, but it's going to work. So let me show you what that would look like with long division. So with long division, I'm going to take x squared minus 1 and divide it by x plus 3. So x goes into x squared, x times. So x times x plus 3 is x squared plus 3x, and we'll subtract that quantity. So x squared minus x squared, nothing. Negative 1 minus 3x, well, that'll look like negative 3x minus 1. So how many times does x go into negative 3x? Yup, that's going to be negative 3 times. So negative 3 multiplied by this quantity, we got negative 3x minus 9, and we're going to subtract that quantity. So negative 3x minus negative 3x, well, that's nothing. And negative 1 minus negative 9, that's negative 1 plus 9, that's 8. Well, x doesn't go into 8, so then we can add 8, the remainder, 8 over x plus 3. So we have just altered algebraically that rational function to be x minus 3 plus 8 over x plus 3 dx. So then it's fairly simple, meaning it's not totally simple, because the antiderivative of x and negative 3 are pretty obvious, right? That'll be x squared over 2 minus 3x. But then we've got to think about how to integrate 8 over x plus 3. So how would we integrate 8 over x plus 3? Well, let's try a little u substitution. So let's say if u is the entire denominator, x plus 3, then du is a straight swap for dx. So I can rewrite just that one part. Remember, if I have a sum or difference of functions, I can integrate them independently of one another. So it's not like a u substitution that I've got to apply to every single piece, only this piece that I need it for. So that would look like the integral of 8 over u du. Oh, that's right. That fits a natural log pattern. So that would be 8 times the natural log of the absolute value of u plus the constant of integration. And I didn't write anything in there because u is equal to x plus 3, and I wanted to save that space. So there we go. Now, here's a slightly different way to do that same problem, right? That would not require long division. So you can see I got a little qualifier here. You can sometimes use u substitution just straight out of the chute. So I do want to show you what that looks like, just because that's just another option, right? We've got choice, right? That's the name of the game, choice. So if I have the original integral as x squared minus 1 over x plus 3, what I would like to do is set this entire denominator as u. So if u is x plus 3, du again is a straight swap for dx, but then I can manipulate u equals x plus 3 to say that x is equal to u minus 3. Now that's going to allow me to manipulate the numerator, to rewrite the numerator. So let's check that out. So here is the u filter with the little extra bonus manipulator. So I can rewrite this as the integral The whole entire denominator is u. Dx swaps over to du. And now the numerator I can rewrite as u minus 3 squared minus 1. Well, let me show you why this is, some people think, a better option. So now I can expand the numerator. So u squared minus 6u. That would be plus 9, but it would be plus 9 minus 1. It's plus 9 minus 1, so it's plus 8. And that's all divided by u du. So here's what's cool about this, is that if I have a bunch of terms over one single term, I can just divide and conquer. So I can rewrite this as u minus 6 plus 8 over u du. Now things are starting to look familiar, because I can integrate each one of these terms easily. That would be u squared over 2 minus 6u plus the 8 times the natural log of the absolute value of u plus a constant, and then sub back in what u was originally. So that was x plus 3 squared minus 6 times x plus 3, and then the natural log of x plus 3 plus c. Now, here's just a different version of the same answer. And some of you are probably pausing the video, freaking the heck out right now, because these aren't the same. Or are they? They are the same. Now let me tell you why they're the same. If we were to go ahead and multiply out these first two terms over here, let's just look at what would happen. That would be x squared plus 6x plus 9 all over 2 minus 6x minus 18, and then the rest, okay, the 8 natural log, that wasn't the problem. It was those first couple of terms that were the issue. So that's going to be, let's see, x squared over 2 plus 3x plus 9 halves minus 6x minus 18. Now you'll notice that x squared over 2, that part's good. 3x minus 6x, that's going to be negative 3x. Everything's hunky-dory. But then we've got these bonus 9 halves and negative 18. Think about where those might go. Those are just constants. And those constants are actually going to get gobbled up by this unknown constant of integration plus c, because I can add any constant I want right there. And this 9 halves minus 18 is just a known constant that's going to get added to some unknown constant. And guess what that's going to be? That's right, an unknown constant. So even though the formats were slightly different, they are the same function. Well, that's pretty neat. Okay, let's keep going. I got some other examples here that might knock your socks off. How about some trig? Yeah, that's right. I said it. Trig. I hear you shuddering through these earphones. I hear you. Like, oh, trig. Oh. Well, let's see what happens. Yeah, you might be right on this one. What do I do? Maybe some u substitution? What if u is this inside function? Then that's not going to really get me anywhere, because I don't see cosine x minus sine x anywhere to kind of cancel out. What if I just square it? What if I just square it? That's going to be sine squared plus 2 sine x cosine x plus a cosine squared x, all with respect to x. So then, oh, wait. So what if I have sine squared and cosine squared and combine them? That's right. That's just going to be 1 plus 2 sine x cosine x. Now I'm in business, because I can integrate 1 all day. That's just x. Now, how am I going to handle 2 sine x cosine x? I'm going to need some u substitution for that bad boy. So I'm going to do u is sine x. The derivative of that is cosine x dx. And I can actually rewrite that as the integral. Well, I'm going to pull the 2 out. That would be u. And then cosine x dx becomes du. So that integral is 2u squared over 2, which is going to cancel that out, plus a constant of integration, and then stick back in the u, which is sine, so sine squared x, and then there is my antiderivative. Ooh-wee! One more. This one is a classic. Another trig function that if you rack your brain and think about the 6 trig derivatives and antiderivatives we know, there is no antiderivative rule for tangent x. It's not there. You're not going to find it. Now, I know the derivative of tangent x is secant squared, but that's not what we're doing. We're finding the antiderivative of tangent x. So let's see. Oh, well, tangent x is truly the sine of x divided by the cosine of x. Now do you see it? Maybe u substitution will help. Okay, let's try it. What if u is sine x? Okay, if u is sine x, then the derivative of that is cosine x. Watch what happens. Nothing good, because I would get a u in the numerator, and this isn't even cosine x times dx. It's dx divided by cosine x. That's not what I want. Uh-oh, I'm out of luck. So I guess I better go back to the drawing board and set a new u. Well, how about I make u the denominator? Because if I do that, the derivative of cosine is negative sine x dx. I have that. I'm just a negative away from being there. So I'm going to multiply by -1. Well, guess what? I got to multiply by another -1 to make sure that I don't change any values. Send that through the u filter, and I will get negative the integral. Let's see, cosine x in the denominator becomes u. And then all of that numerator, which is negative sine x times dx, right? That is replaceable with du. So I can rewrite this integral as -1 over u du. And that is a pattern. So negative natural log of the absolute value of u plus the constant, and u is cosine x. And ladies and gentlemen, what a fun problem the integral of tangent x is. Oh, what a joy. So this thus ends some more complicated versions of u substitution. Hope you enjoy. One more to go. See you soon.